Welcome to another video. In this video, we are going to talk about Vandermonde determinants, which we'll need in a lemma towards proving Tau's uncertainty principle that we're working towards very, very slowly. So remember, in the previous two videos, we talked about cyclotomic polynomials. So that won't come up in this video, but it will come up in the next one in conjunction with Vandermonde determinants, which we'll define and prove some properties of today. Okay, so let's just jump right in. So Vandermonde determinants are polynomials delta n. They're indexed by n integers, positive integers, and defined by, so I guess there's no and, defined by, so delta n z1 up to zn is equal to this product. We take all I less than j, and we take zj minus zi. Okay, so this doesn't look like it's certainly a polynomial. Okay, it's a product of n choose 2 linear polynomials. But you might be wondering, why is it called a determinant? Well, the next lemma shows why this is called a determinant. Okay, so we're going to prove a coefficient formula for Vandermonde determinants. So lemma. So let z1 up to zn be complex numbers. Okay. Let v, so v is going to be a matrix. I'm going to give myself space. And it looks like this. The first column is all ones. The second column is z1, z2 down to zn. Then we get z1 squared, z2 squared, all the way down to zn squared. Okay, I think you can see where this is going. We're going to get zn. Oh, sorry, it's z1, right? Because the first row is all z1. So z1 all the way up to n minus 1. z2 to the power n minus 1, sorry. And all the way up to zn to the power n minus 1. Okay, so that's v. Okay, so the lemma says we have delta n z1 all the way up to zn is equal to the determinant of v. Okay, so proof is not too difficult. So we need to know the formula for a determinant. It's actually called the Leibniz formula. I didn't know that until now, but we'll call it that, the Leibniz formula. Even if you don't know that it's called the Leibniz formula, you no doubt know this formula, like you used it before in 2x2 matrices and 3x3 matrices, at least. So for determinants, okay, the determinant of v is equal to the sum over all permutations pi on n letters, the sine of pi, and then a product of I equals 1 to n zi to pi I minus 1. Okay, and this is just okay, so you've seen this formula is a really fancy way of saying, you know how when you get a determinant like this, what you take is 1 times the determinant of this matrix here. I think you can see my mouse. I really hope you can. And then you take z1 times the determinant of the matrix if you delete the column and row. Sorry, the column and the row of z1, but you have to minus, like you put a minus sign. So that's the sine of pi here, right? So you're kind of like alternating between, and then so maybe I'm not explaining this the best way, but you've seen that formula before, and what you're doing is you're recursively computing this sum here. Okay. Okay, so where Sn is the symmetric group of all permutations on n letters, sine pi here is the sign of a permutation. So you might recall from an algebra class that every permutation can be written as a product of transpositions, and the sign of a permutation is +1 if it's an even number of permutations, and -1 if it's an odd number. Okay, now so since the ith column, should really say the jth column, shouldn't I? But whatever. Okay, since the ith column of V contains only monomials of degree I minus 1, every term of determinant of V is a monomial of degree, total degree. N, well, I'll just write it out. So it's 0 plus 1 plus all the way up to n minus 1, which is equal to n minus 1 over 2. What is it saying? It's saying every term in this sum is some kind of product where you take one element from each column, but each element, each column contains column I contains elements all of degree I minus 1. So when you add it all up, it's going to be degree 0, degree 1, degree 2, all the way up to degree n minus 1, and that's n minus 1 over 2. The total degree is the sum of all the degrees in a monomial. Okay, so in the formula, so this is the other formula. So we're trying to show two formulas are equal, right? So Z1, Zn equals, this is the product of I less than j, Zj minus Zi. The product, so since the product runs over n choose 2, which is the same thing as n minus 1 over 2 linear factors. Okay, every term in the sum is a monomial of total degree n minus 1 over 2. Okay, so all the degrees already check out, but we know a little more than that. Let me just flip to the next page here. Okay, now because the determinant of V is 0, I wrote equals and is equal to 0 whenever any two of the Zi are equal. Okay, the determinant of V is divisible, sorry, writing equals, is divisible by Zj minus Zi, right? So if any two of the Zi are equal, so Zj equals Zi, meaning, so sorry, Zj minus Zi, so sorry, let me just think of this. So when any two Zi are equal, determinant of V is equal to 0, right? So we have a root of the determinant of V whenever two Zi's are equal. That's also a root of this polynomial right here. Okay? So this polynomial divides determinant of V for all I less than j, and dividing all of them out, we get a polynomial AL f such that determinant of v is equal to delta n f for some polynomial. Well, what am I just saying? I just said for some polynomial twice. Okay, cool. Now, okay, now since both of these they consist of monomials of degree, total degree, n choose 2, we can't actually, this f has to be constant. Okay, does that make sense? If f was like not a constant function at some degree, then you'd multiply them and then the terms wouldn't have the degree that we already computed they have. So f has to be constant, and we just want to find out what constant. In fact, we're going to show that it's 1. We just take, so in the term corresponding to the identity permutation in the formula, that's his formula, for the determinant of v is, well, because we take, where's the sum again? Big sum, yeah. So the identity permutation, so pi I is just I, so it's zi to the I minus 1. Okay, and so we get z2 I minus 1, right? So it's just to the 1, and then z3 squared, z4 squared, all the way down to, not squared, cubed, all the way down to zn to the n minus 1. And then also, and expanding delta n z1 all the way to zn, which is z2 minus z1, z3 minus z2, z3 minus z1. You can see the pattern here, so z4 minus z3, all the way down to zn minus z1. Okay. We see that the first term here is the same. Okay, so it's literally the same thing. There's no coefficient, so f has to be 1. Okay, and yeah, right, so z2, z3 happens twice because there are two things less than z3, and then z4 happens 3 times, zn happens n minus 1 times. So that first, by first I mean, this multiplying all these first terms together, you get exactly this monomial. So that constant, that factor f is 1. And so they're equal. And that it's pretty simple proof. And the reason I'm even doing this is because it's the next computation is actually quite technical and annoying, and this is kind of the first step of it. So explaining it with something easier will help us understand the next proof. Okay, so now we're going to need a coefficient computation. This is kind of technical, and honestly, if you were to skip any part of this whole series, you probably could skip this. It's an interesting proof. It's just like the result is kind of all the gross parts of the next lemma have been like put into the, next lemma. So we're all building up to something called Chebotarev's lemma, which is really a theorem. I don't know why it's called Chebotarev's lemma in the book that I'm following. We're building up to prove that theorem, right? And so all the annoying parts of that proof have been kind of put into this lemma here. So maybe wait for the statement, but if you don't feel like, I don't know, whatever. You can do whatever you want. It's okay. Okay, so we need a coefficient computation. And the coefficient computations, not on Vandermonde determinants per se, but they're actually about these generalized versions of Vandermonde determinants, and I'll show you exactly what I mean. So lemma, let n1 up to nk be positive integers, and let p in z1 up to zk be the polynomial given by, okay, it's kind of disgusting formula, so z1 up to zn is the sum of all pi in sk sine pi the product I equals 1 to n of zi n pi I. Okay? Now this is very, very close to what we had before, except before we had pi I minus 1 for n pi I. Right? So if we set ni to I minus 1 for everything, then we'll have exactly the same thing. But as you suspect, this is a determinant of something. Okay? So that's why these are generalized Vandermonde determinants. So this strictly, sorry, this the Vandermonde determinants above are included in these kinds of determinants here. Okay, but what does the lemma say? Then we may factor P equals delta K Q. Sorry, I'm just going to move this, it's shaking. Where Q in Z1, there's not enough space here, but you know what I'm going to write, Z1 through Zn, is such that Q of evaluated all at once is equal to delta K N1 up to Nk over delta K 1 up to K. Okay? So this is see. The proof is actually like legitimately quite interesting. It's just that this statement's not very interesting, and it's clearly just a lemma that we're going to need later on, and that's why we're doing it. Okay. All right. Let's just do it. So proof. Yeah, we're gonna show later on that some coefficient. Sorry, where's my mouse? It's actually eerie. My mouse is gone, so I don't know how I'm gonna stop the video later, but at least I can still write. Okay. So by the Leibniz formula again. P z1 up to zn is the determinant of the matrix zj and I, or zi to nj, it doesn't matter really, because okay, am I gonna have to scroll like this? Like what actually happened to my mouse? That's really bad. Okay, I'm just gonna have to go down with the arrow keys at the moment. Sorry about that technical problem. But we soldier on. As in the previous lemma, okay, because this is a determinant. This is a determinant, so P vanishes whenever any of the Zi are equal. So P vanishes when Zj equals Zi for any, I guess, for any I less than j. So P, we won't do the whole thing again. P is divisible by the kth Vandermonde determinant. Okay, I'm gonna write that whole thing again for some polynomial Q. Okay, so we've found the existence of this Q, and that's the easy part. So a factor, that's something we had to prove. We've done that. We just need to now compute Q evaluated at all ones. Let's write that. It remains to compute Q of 1. Okay. So to do that, consider the differentiation. So it's the normalized differentiation operators. We're gonna call them DI. Now, some people use that for the differentiation, like the partial differentiation operator in the variable I. Anyway, but we're not gonna do that. We're gonna do that scaled by Zi. So dzi. Okay, so like for example, d d1 of like z1 squared, z2, z3 cubed. Well, that's equal to, you take the derivative with respect to z1, right? So that's d1 of that. Take the derivative with respect to z1, which normally gives you 2z1 z2 z3 cubed. But now we times z1 back, so the exponent doesn't change. Okay, so it's very interesting. We're basically taking just the exponent and multiplying the whole thing without changing the exponent later on. Okay, so that's an example. So it's easy to see. In fact, we just did it, and as an example, that these operators. Oh no, sorry, we didn't just. I thought I was about to say something about whatever. It'll come back up later. We first can talk about the product rule. So these operators obey the product rule. So di of two functions multiplied together is equal to f di of g plus g di of f. That's just the product rule, and you just multiply by zi, which is obviously linear. So it distributes over that sum. Okay, now this is what I was going to say. So since di z1 to the n1 all the way up to zk to the nk is equal to ni of the exact same thing. Okay, this monomial is an eigenfunction of di with eigenvalue in I. Okay. Now, let's consider this polynomial. So d2, d3 squared, d4 cubed, d5 to 4, all the way down to dk, the k minus 1, of p. So we're taking p, and we apply them in reverse order, right? Like from right to left. So we first differentiate it by dk, k minus 1 times, then we do k minus 1, k minus 2 times, and so on. This is the same thing as d3 squared dk of this product, right? Because we factorized it into a product of the Vandermonde determinant and q. So I'll put q first, times this, I less than j, zj minus zi. Okay. Now, if you'll notice, sorry, this is k minus 1 here. So this is the function, and okay, we want to actually evaluate this at 1. Let's just write that. By 1, I mean all ones. Should write that. Same thing. Okay, let's think about what happens. So there are k choose 2 differentiation operators here, and there are k choose 2 linear factors, and then plus 1 plus another q here. Okay, but because we're evaluating it all ones, all the zj's are going to equal all the zi's, which means that this is going to be 0 unless we somehow use the differentiation operators to neutralize the factor zj minus zi. Now, the only thing that can neutralize zj minus zi is if either dj or di hits this linear factor. Okay? Now, it's kind of I'll try to write that out. So repeatedly applying product rule, we get, okay, every time we apply the product rule, it doubles the amount of terms, right? And so we get 2 to the k minus 1 over 2 terms. Okay, but we just said the only terms that survive the evaluation at 1 are the ones in which all these differentiation operators didn't land on Q. They in fact landed on these linear factors. They're exactly the same amount, so all of them have to land on them in some way, in which all the operators land on all the linear factors. Okay, but they have to land on the right ones too. So, oh boy, how am I gonna make a new page without a mouse? So, sorry about this. Let's just try like Control N. Oh, that's not good. Cancel. That was scary. New page, Shift Control N. This is really sad. I have a mouse somewhere. I wonder if this is you subscribe for. What are you doing? You get to see me wrestle with missing cursors. I plugged in a mouse and now it works. And what if I unplug the mouse? If I unplug the mouse, it doesn't work. So the oh boy. Ho-ho. Okay. Hi, welcome back. So what actually happened is my computer crashed after I plugged in the mouse and then started clicking everywhere to get like a million new pages. It crashed. What's good is that before it crashed, the recording software saved the video I had done so far. But what was bad was that I actually lost all the writing I had. So you can see everything up to here has died. This is from the previous video. And so what I'd written down for the proof has disappeared. But it's okay because it was recorded, so you can just skip back to find it. And I'm just gonna continue where we were, which is we're trying to prove that Q evaluated at 1, all these ones is equal to this. Vandermonde determinant evaluated at n1 through nk over the Vandermonde determinant evaluated at 1 through k. Okay, so we're just going to continue. So we were considering this these differentiation operators acting on this product, which is equal to p. Remember, this is p. And we were saying that by the product rule, there are lots of terms, 2 to the k choose 2 terms. But the ones that are non-zero are when all the operators land on the correct linear factors. Okay? And what does it mean by correct linear factors? Well, so remember so we need di to land on either zj minus zi, in which case you'd get a minus zi, or on zi minus z something else. What's before I? H. That's really weird. Let's just say this. Zi minus J, and in which case you get plus Zi. Okay? So we need I to land on all of these. So notes. Well, we want to count how many ways this can happen, right? So there's actually fewer ways than you think. So because all these dks have to land on something that contains a k. Okay? But in this product, there are only k minus 1 things that contain a k. So all the dk have to land on the zk minus zi factors, of which there are k minus 1. So there's actually only, there are k minus 1 of these, and there are actually only k minus 1 things that are allowed to land on But they can land in any order, so of which there k minus 1. So there are k minus 1 factorial ways this can happen. Okay, and then now we've done that, and we're going to do dk minus 1. Okay, now, so with that done, there are k minus 1, or sorry, k minus 2 instances of dk minus 1, and exactly k minus 2 undifferentiated. Differentiated linear factors containing the variable z, k minus 1. Okay, so, well, so there are, sorry, and before, remember, this is zk, so zk is positive here, so it yields a zk, not minus zk. Up here, because zk is in the front spot, not the minus spot, it's a plus zk. So there are k minus 2 factorial ways this can happen, and yields z k minus 1. Okay, and now we continue. So we continue in this way. Continuing, we get so this thing d2, d3 squared, d4 cubed, all the way down to dk k minus 1 of q in this product less than j. So j minus zi, sorry. This thing, okay, evaluated at 1 is equal to 0 factorial, 1 factorial, 2 factorial, all the way up to k minus 1 factorial. When you go backwards, okay, times, right, we never hit q at all. So all the operators hit the linear factors, we never hit q, so q remains the same. It remains untouched. Okay, but, well, this is because we evaluated it once. So remember, all the differentiation always yielded that first term, so zj or whatever, but then we made zj equal to 1. So this should make sense to you. And now we realize that, look, so dk of 1 up to k is also equal to product of I equals 1 to k, obviously. All the j's greater than I, okay, of j minus I. Okay, so, and of course this thing is just, is this j or is this I minus 1? Yeah, I might have done this wrong. So there's j here. Okay, I think this is better. So j equals 1 to k, j minus 1 factorial. Okay, and that's exactly what we have here, right? Okay, so we've shown so we've shown that d 2 d3 squared all the way up to dk k minus 1 of p evaluated at 1 is equal to delta k cubed 1. Okay. Yeah, so let's make a new page. Sorry, this is delta k, not what have I done? New page. I messed this up. This is lots of little errors in this video. Sorry for the imperfection. Okay, so P delta K Q. There you go. So Q1. All right, now we note that okay, we can also do this this computation differently. So we defined P earlier. I gotta rewrite that definition because I can't scroll to find it. So we defined P to be P Z1 Zn equals the sum of all pi in Sn sine pi product of I equals 1 Z up to n Z I n pi I. Okay, so we have this. Okay, and if we apply these operators, we already know what these operators do to a monomial like this. So each of these is a monomial, right? We take a product of a bunch of zi's. It's a monomial, and we already know that this monomial is an eigenfunction of di. So we know exactly what it does. So dk, it's an eigenfunction with eigenvalue nk, right? So or n pi I. N pi k. Yeah, sorry. It's an eigenfunction of di with eigenvalue n pi I. Okay, so we can directly just compute that d2, d3 squared all the way to dk, k minus 1 of p, okay, of z1 up to zk is equal to the sum of pi in Sn sine of pi product of I equals 1 to n pi I to the I minus 1 zi n pi I. Okay, so it's to the I minus 1 because of how many times we apply it. It's an eigenvalue with it's an eigenfunction with this eigenvalue, and we do it I minus 1 times. So we get yeah, k and I are kind of being used. Yeah, k is where it ends. Sorry, this is a k. Yes, okay. So now we evaluate at z1 equals zk equals 1. And so this disappears, right? And note that we can take the sum over all pi inverse. I'm going to rewrite it here and show you. So pi in Sn, you can take the sine of pi, because the sine of pi and the sine of pi inverse are the same. So take the sine of pi, but now in I equals 1 to k, we can replace pi I with I and I with pi I. So we get n I to the pi I minus 1, z pi I n I. Yeah, and I, but this disappears, right? So it doesn't really matter. And this is exactly, okay, this is exactly equal to delta k n1 to the nk, right? So we replace the sum over all pi to the sum over all pi inverse, which is okay because the sign stays the same, and then we just switch I and pi I. And we get that. Okay, so what we've shown, we combine that with this here, we've shown that delta k, so delta k n1 all the way up to nk is equal to delta k 1 up to k times q of all 1s. And now we just divide on both sides by this, which is non-zero, because these are all different. And we get exactly the coefficient computation that we desire so greatly. Okay, sorry for what was kind of an unfortunate video. With any luck, you actually skipped all of this because I told you you could. But this is a bit of a, it's just annoying. Yeah, I can't even pull up the, sorry, can't even pull up the statement anymore. The statement is just super technical. I'll restate it in the next video. In the next video, we're going to prove Chebotarev's lemma. And Chebotarev's lemma kind of combines together everything we've been doing. So we had some properties of cyclotomic polynomials. What is that? 2 videos ago now. Then we proved the irreducibility of cyclotomic polynomials. And then we have Vandermonde determinants and even these generalized Vandermonde determinants. And so Chebotarev's lemma will tie together all those things into like a neat package that we can then use to prove Tao's uncertainty principle. Okay, so all of this has been to prove Chebotarev's lemma, and in the next video I will restate everything we need to know about cyclotomic polynomials, about Vandermonde determinants, to prove Chebotarev's lemma. Okay, I will see you then.